our last topic, our last collection of lessons here is about solving exponential and logarithmic equations. I think if we talk through that topic and sort of get you to where you're able to handle those without too much of a hassle, I think we'll be able to call that a semester. So this will be particularly helpful for you if when you go into the calculus sequence, solving exponential and logarithmic equations. I'll try to pick out a few that are particularly helpful and kinds of things that you're really likely to see in the calculus sequence. But okay, a couple preliminaries for solving these equations. A couple of maybe a few building blocks to bear in mind here. One of the properties of logarithms. So the properties of logs is that the natural log, again, I'm going to use natural log. Typically everything you do in the calculus sequence involves natural logarithms. So I'm going to go ahead and limit myself to natural log. The natural log of A plus the natural log of B, and this can be either a single variable or a larger expression. If you have the sum of the logs, that's the log of the product. You may combine two logs. Adding logarithms combines into the log of the product. And, oops, sorry, let's try that again. And if you subtract the logarithms, it follows a similar pattern. This is a divide by b, so this allows you to combine two logarithms into one. That's going to come into play when we solve the equations. And then the third property allows you to move this exponent as a coefficient. So this is n times natural log of a. And so those are a couple of preliminary pieces of information, the properties of logarithms. Now, the relationship between the logarithm and the exponential function, remember that the natural log, and I'm going to do this conceptually, not an official way that the textbook would write this. Natural log of e raised to the power of some stuff. The natural log of e raised to the power of some stuff is equal to, it is when you apply natural log and exponential in sequence, they're inverse functions. It is as if they cancel out. And you're left with just the stuff. More to the point, if I have natural log of e to the a, that's equal to a. So the natural log and the exponential are inverse functions. You're left with just the argument. Whether it's a single variable or a larger expression is irrelevant. And then similar to this is e raised to the power of natural log of some stuff. It doesn't matter the sequence. So you can do natural log of e raised to the stuff or e raised to the power of natural log of some stuff. Again, these are inverse functions applied in sequence, and you're left with just the stuff. Again, this is not what you'll see in a textbook. You might see something a little more along these lines. E to the natural log of a is equal to just a, where a may be any expression. So we have the inverse function properties, and we have the ways to combine or decompose logarithms with the three basic properties of logarithms. Now, one last little piece, I want to review something that I think you all know, but we're going to be using it in a slightly different, maybe a little unfamiliar way. I want to talk about the quadratic formula. But what will very often occur is something like this. You might have something, you want to solve for x. Now we know the quadratic formula. X is equal to negative b plus or minus square root b squared minus 4ac all over 2a. Remember, this minus is here because of the formula. The 4 is here because of the formula. But the key is, these a, b, and c are the coefficients. So if we have a, x squared, plus b times x plus c, for one thing, it must equal 0. If this is not equal to 0, then this is not correct. You may not use these values if this is not equal to 0. So step number 1 is to get it equal to 0. And then whatever the coefficient is, whatever the coefficient is, whatever the coefficient is, those values go into here. The coefficient could be a simple number, or it could be something a little more elaborate. Consider 3x to the second minus, let's say, 4 times the natural log of 2x minus 5. So this is equal to 0. This is quadratic. But notice, a is no problem. A is 3. C is no problem. What is C? C is not 5. C is negative 5. The sign goes with the number behind it. And the question now is, what is B? B is this large expression. B is negative 4 times natural log of 2. Write that as if it were a single number, and then at the very end you'll compute this out. So let me go ahead and see if we can solve this out as practice. And then we'll also, I have a calculator here, we'll also compute the decimal approximation. So we know x is equal to negative b. Wherever you want to be, you put negative 4 natural log 2. So negative is because of the formula, negative because that's what the value gave, the equation gave to us. Negative b plus or minus square root b squared, negative 4 natural log of 2 quant squared minus 4 times a times negative 5 is c, all great big honking over 2a. Now what is that? That is, negative is positive 4 natural log of 2 plus or minus big old square root. Just write this as quantity squared. One thing you may do is, if this is negative, notice the square gets rid of the negative, so we may drop that out. This is, can we see this is 4 squared? 4 squared, negative 4 squared is 16 times natural log of 2 squared. Maybe we'll just do it this way. I'm going to write this as 4 natural log of 2 quantity squared. And don't worry about trying to compute that. Well, I did get rid of the negative sign because we deal with the negative squared cancels. Then I have negative 4 times negative 5. Negative 4 times negative 5 is positive 20 times 3 is 60. All over 2 times a. And then once we have this, this is the exact value. When we talk about exact values, that's without computing these. But now we can say this is approximately equal to, and now we can get a decimal approximation. So I have 4 times the natural log of 2. That's, I'm going to use a 2 decimal approximation, 2.77 plus or minus the square root of, this is now 2.77 squared. And that's I'm going to approximate that 6.69. I'm sorry, that's wrong. 7.69 plus 60 all over 2 times 3 is 6. And so now you can compute this the rest of the way out using 7.69, 2.77. We have our plus or minus. And so you could go ahead and compute this out and find the specific decimal approximations using those values. So when you plug values into the quadratic formula, use this larger expression and just carry it along for the ride until you get to where, now we're at the point where you need to get the decimal approximations to do the actual computation. So we've had some preliminaries here. We had the basic properties of logarithms, we had the inverse function relationships, and then we also had the quadratic formula. Be careful. It could be that this coefficient here could have something larger involved. It could be that this have something larger involved. So any mix is possible. I'm going to throw one more of these at us and see if we can figure this. What if we want to solve for x? What if we have x squared minus e times x, not e raised to the x, e times x, and let's say that's minus 1 is equal to 0. Well, this is a number. Don't use a decimal yet, so we do know x is equal to negative b. Do we see negative b? B is negative e, negative b, plus or minus square root b squared minus 4 times a times c all over 2a. So this is now positive e plus or minus. Whenever you have a negative squared, you can square the negative out. This is e squared. This becomes plus, right? Negative 4 times negative 1 is plus 4 all over 2a. And then we can get a decimal approximation. Let's go. If a way to find e, some of you have an e button on your calculator. Another way is to go, if you have the e to the x key and raise it to the first power. This is 2.72, we'll say. This is now a brutal approximation. Again, what I did was I took my e to the x button, I took e and raised it to the first power. Plus or minus. Now I need e to the second power, so e to the x to the second power. This is I'm going to approximate that 7.39 plus 4 all over 2. And that, I'm going to bring this over here. So that's 2.72 plus or minus, I'm going to take the 7 plus the 4, 11.39 all over 2. Now, so I can actually go ahead and compute this all the way out. This is 2.72 plus the square root of 11. Well, let's do this. What's the square root of 1139? So add the 4. The square root of that, again, depending upon where and when you round, this is approximately 2.72 plus or minus, I have 3.37. If you have 3.38 or 3.35 or 3.36 or something close, that's okay. I'm not going to be concerned with tiny little round off differences like that. All over 2. So we have 2.72 plus 3.37 over 2, or 2.72 minus 3.37 over 2. And you compute the plus and the minus. So if I'm going to add 2.72 and divide the 2 out, that gives me approximately 3.05. And then let's clear that. Let's just do this as a dirty approximation. 2.72 minus 3.37 equals, and divide that by 2, and I have negative approximately 33. So the specifics aren't important, but it's this notion of if you have an expression rather than a concrete number, just carry the expression along and then eventually get a decimal approximation and compute the quadratic formula from that. So that's a little bit of a brush through of some previous work, and now with our next videos we'll go ahead and continue on solving the actual exponential and log equations.